Right. Come on again, students. What I'm saying is that I'm very upset with the fact that the students, so many students not producing any work. I know the teachers in the schools complaining of exactly the same thing, that they're not getting work from the students. 30% and 20% of the students doing work and submitting work. So in addition to not attending the classes, they're not doing the work. Right? The advantage with this class is that the classes are recorded and it's available for about a week. And therefore, if you don't get a chance to attend the class for whatever reason, because we know people have internet problems and all these things. We know that there are challenges out there. So if for whatever reason you're not able to attend the class when it is held, at least the video is there. The beauty about attending the class, the actual class, is that if something comes up, we can ask a question, right? And not just depending on our video. And so that's the beauty about actually attending the live class. I know that the recordings might be good, and I know that I try my best to explain everything, but still sometimes there are questions that they might ask. But some person not asking any questions anyway. So it's basically the same persons who ask questions and interact in the class, the same persons who sending work. There are a few persons who might not say anything in the class, but trust me, they're sending the work. And then there are some persons now, I'm wondering if they just join the class, turn off the video while after I start, and just don't pay attention and just don't do anything at all. I don't know. It's not the classroom. I am operating blind here. And as I said, I'm not going to put my reputation on the line for students who are not cooperating with this program. Next thing you know, I normally get like over 90% pass. Next thing you know, this year, my pass rate dropped down to 10% and 30% and 20%. Simply because some of you decide that you're not doing the work. I'm telling you, the only way to gain success in the subject is to do the work. The only way. There's no shortcut. There's no roundabout method. That's the only way to gain success in the subject. I'm certain that you're all in this program because you feel like you need assistance. You need the direction. Some of you have good natural ability, but still you need the direction. You need to know how to prepare and stuff. And some of you, you're not very strong. You're very weak in the subject. Right? That is just a fact of the matter. There's nothing wrong with being weak in the subject. Not a thing wrong with that. I've had students join my program who are averaging 15% and 10%. And at the end of the day, they come out with a grade 1 because they put in the work. Right? So I'm not feeling good at all about this program right now. And I feel as if there are a lot of advantages to the online. But the big disadvantage is that students, I'm operating kind of blind, and so many students not cooperating and not producing the work and not sending solutions. And therefore, there are a lot of students in the class. If a parent asks me, how is my child doing? I cannot say a word. I don't know. And usually in the classroom, I'm able to say, all right, he's coming on, he's that, or she's this, or she's that. In the classroom, I'm able to say something. Parents will send and ask me, how is my child doing in the class? So what does that mean? I cannot say anything. I don't get any questions in the class. They don't participate in the class, and I don't get any work. Right? So the main thing I can depend on right now is the actual work. In the classroom, I can look at somebody's face and see if they understand. I can see it. I can see that they understand, or I can see they don't understand. I can see if it's a struggle. When I give work to do, I can see how long it takes to do it. And when they bring the work to me, I can see the direction that they're going in. I can see if they're strong on the topic or they're not so strong on it. They need more help and they need more work. Students who need more work, I usually find a way to give them more work or give them more assistance. I'm not able to do that here with a lot of you because they're not giving me the assistance that I need to help you. Right? So my only solution right now is to save my reputation so that when COVID finishes, when COVID is over, I will go back to normal classroom situation. When I can go back in the classroom and go back to my normal way of delivering this thing, I will still have my reputation intact. I don't want any year my percentage pass rate fall below the high standard that that I'm used to getting for many years. For many years. Even years when people come and complain or the exam hard and this and my students still acing it and getting the high grades. And this is the year now I'm at greatest risk. I'll put my reputation at risk like that. I intend to be teaching mathematics until I'm dead, because it's my first love. Teaching mathematics is what I like to do more than anything else. Right? And therefore, in order for me to get students to teach, I have to have my reputation up. It's a pride for me. It's a pride for me, something that I enjoy and something that I look forward to, and I look forward to exam results every year. I don't want to see exam results when exam results come out. I say one bag of cheese. Cheese not a pass grade for me, you know. Cheese come like a fail grade to me, you know. Right? And I like to see the majority, over 60% on average of my students, over 60% of my students must be getting grade ones. Right? Another 30% getting grade 2. And then now, very weakest students who really have it hard and difficult, still manage to get a grade 3, at least. Students who are really struggling, right? Who the background is so weak that you have to do a lot of work to bring them up. But still, we usually get people over the hump. So in a year when I have like 80 students or so, 90 students, I might find 1 student or 2 students who get grade 4, and usually those are the students who don't participate, don't cooperate, don't follow the instructions, don't come to class, don't do the work, and all these things. I can't live with this 1 or 2 students like that, and I usually talk to the parents and let them know. So normally when they get that grade 4, the parents don't say anything to me, because I already warned the parents that the student not participating, not cooperating. And I can tell the parents that, boy, no, they're not keeping up. And the main reason usually is because they don't do what they are told. Right? So I put in all and warning now that soon I'm gonna start, just putting persons out of the class. Just take you out of the group. I send a message to your parents and let the parents know that you're not participating, you're not attending the classes, you're not sending any work. And I'll just put it out the group or the WhatsApp group, and that is it. As simple as that. Better I have 5 students teaching more than 30 and 40 students, with 35 of them not doing any work. Better me I just have 5 students, I'm getting 5 straight A's. I'm gonna feel better. That will be a 100% pass rate anyway. You understand? So that is what's going to go. Remember, guys, this is not my only job. So if a lot of you feel like I'm depending on the money from this work, from teaching, that is not so. I'm an engineer. I work otherwise as an engineer. Teaching is not my first profession. Teaching is my first love, but it's not my first profession. So I work otherwise. So it's not like I can't live without your fees. If you notice, my fees are very low in comparison to what I deliver. Because I give you 3 classes and 4 classes if I need to on a week. And I don't watch time on all these things. And the only reason why I charge for the most part is because everybody is charged. So I have to charge as well. You understand? For 20 years I taught without pay, for free, 20 years I teach for free. Right? And I realized that in a sense I give away my ability, and I'm doing such a great work, doing such a great job, and going so hard and do it for free. And you must, and generally speaking, I can teach you something, tell you something. Anything that you are good at and anything that you are the best at, you must not do it for free, because that is your God-given talent. You must not do it for free, especially when other persons who are not as good as you doing it and earning from it. And that's why I decided to charge for my classes. But that's not my first priority. My first priority is to impart the knowledge and to get students to do the very best work. That's my first priority. Understand? So if some of you feel like because you're in the class and you're paying a little small fee, because just type in you're paying me, can tell you that, you know, stipend compared to the hours and the time and the effort and the material that you get. I'm charging you a stipend. I'm charging you almost nothing for my time and my effort and my material. And you'll see even more because you notice, for example, you all got a session yesterday that is not charged for. And when we get into March, you get far many more sessions that you're not paying for. So this is not about the money. So some of you feel like because you're paying, right, you can do anything. It don't go that way. Not in my program. Because you're not gonna pay me, and at the same time you're killing my reputation. I'm not taking anybody money for them to kill my reputation. Not going to happen. You understand? So this is a very serious program. If you join this program, you have to be very serious. It's not a joke program. I don't care about what other people are doing. If you join this program, I expect you to do the work. You know, far reach already. We do that. We do some past papers yesterday. You know, and you see the number of questions that we were able to go through on that past paper and those past papers. It means that we have gone a far way in the syllabus. Right? And some of you don't send me no work at all from the start September up to now. No work. No work I get from some of you now. That doesn't make no sense. And it's not going to continue. I'm telling you. So from next week, I'm going to start issuing my notice to persons. I start issuing my notice. This little classwork here, so after the 2 weeks of transformation and 2 weeks of practice and do so many questions. And so many of you, we make sure we're going to easy one question, transformation question. Easy. 4 easy little parts. And you can't find the time. We just wrote the little transformation question and send it. So we can see if you're learning or not learning. You can't do that. Well, all right, I'm going to show you what you can do. If you don't do the work, you're going to put it out of the class and find another class. Right? If you can't do the work, you're going to find another class. Understand me? I'm going to save and protect my reputation. You can go another class and get your 1 with straight A's. I'll be very happy. You get a 1 with straight A's by attending another class. I'll be very happy. But I'm not taking the risk. I'm not taking the chance. I'm not allowing anybody to put my reputation at risk for some little stipend fees. Not going to happen. Because as I said, what they're charging for this class is a stipend in comparison to the amount of material and the time and effort that I put into this program to help you gain success. Understand? All right, so that is it. So from next week, send somebody a notice yesterday, and I sent a notice to one parent yesterday, that I'm going to put the student out of the class. Right, and the parent saying the student said they're attending and they do work and whatever. So all right, I give them 1 more week chance. But the only reason I decided to continue, I allow the student to continue, because I did not give this notice first. So now that I give this notice and everybody know what I'm up to, when you hear me say you are out of this program because you're not producing any work, then you know that that is it. I mean, in the second chance business, because everybody get, I don't have time for that. I don't have time for that. Second chance, and people call me and I beg and I say, sir, give them another chance. And no, not into that. When me say that's it, that's it. Because I've been preaching the same thing since September. Do your work, send it to me. Do your work, send it to me. Right? I've been preaching the same thing since we started. And persons just ignore it and not doing any work. All right? So I'll cut this class down to 5 persons and we'll enjoy ourselves. Understand? 5 persons are the 10 persons who are serious. I work with them. All right. Enough of that. So you know what I'm up to now. So I will know who's serious about being in this program and who not serious about being in this program by the word that you send me. That is how I know. All right. That is that. All right. So let's look at the classwork. All right. So this was the classwork. It's a past paper question. The only part of it that was not on this exam, on the past paper, the only part of it that was not on the past paper, the only part of it that I put in was this part of it. I put that part of it in there. So when this question was set, only these three parts were in there. The actual exam question. Simple as that. I am the person who put in part 2. That says state the effect of V on the triangle. Because the reason I did that is because the V is an enlargement, right? And I wanted you to focus and know how the enlargement took place when I said the effect. In other words, what happened to the triangle. All right? So let me go. So the question said, the vertices of a triangle are A12, B11, and C21. Those are the vertices of a triangle. It says ABC undergoes 2 successive transformations, V followed by a W, where V is this one and W is that one. And the question proceeds to ask to describe each transformation, V and W. Describe each of them. So in order for you to describe them, you have to know them. All right, now let's look at the V. Remember now, all the transformation matrices that we looked at, them have 1, 0, -1 in them, except for the enlargement matrix, which is K0, 0K. All other matrices, rotation and reflection that we looked at, them have the values 1, 0, and -1 in some form of combination. These are the values. This one has -2 in where the K would normally be and where the K would normally be. So therefore, that's an enlargement transformation. Some persons be telling me it's rotation and reflection and all these things. All right, so that is it. Learn from your mistakes. So V is an enlargement and the scale factor is -2, and it is an enlargement about the origin. All right, and then this one now is the clockwise 90-degree rotation about the origin. So I'll say the -1 down here. You have to learn the matrices. I think almost everybody got that one who did the question. All right, so what do we write? Let's write it. For part 1, you can say V colon. What is V? V is an enlargement of scale factor -2 as a scale factor about the origin. That's it. What have we given? We have given the name, the enlargement of as two components, a scale factor and as a center. That's the center right there. The center is the origin. When you know that the center is the origin, you call it the origin. Don't just keep calling center. I'll tell you what I mean when I get to that part. All right, so that is it. So that's your description. Some persons you could give the name and then give the and then just list the components. You could just list them. All right, so the center is the origin and the scale factor is -2. I can write that as a sentence like that. All right, once you give the scale factor as -2 and the center as the origin and say it's an enlargement, you're good. You don't have to use these exact same words. All right, W. W is a 90-degree clockwise rotation about the origin. Let's check, make sure I cover everything. Give the name and the components, 3 components: angle, direction, and center. So give the name and the components. See, one person left out this part. One person left out this, the center, which is a common mistake. Right? So learn from that mistake. You have to give the angle, direction, and center with describing a rotation. That's the answer part 1, you know. You could have listed it, you could have said it's W is a rotation. Angle 90 degrees, direction clockwise, center the origin. Could have said it like that. All right. Part 2 now I realized that some person looked at the Muslim sheet to answer part 2 because they basically copied the wording of the Muslim sheet. Right? So I still don't know if some of you really understand what is happening. So how does it work? Right? So for the enlargement of V, it's an enlargement, the scale factor is -2, and the center is the origin. So you're going to describe what happens to it. You describe it in reference using those. Right? All right. So let's look at what the scale factor of -2 does. First you talk about what the 2 does. The 2 does 2 things. It causes the image, the sides of the image, to be twice as long as the size on the object. So the image is twice as large in size, or not size, in terms of length. Right? So the image, in terms of length, the image is twice as large or twice as long as the object. The size on the image are twice as long as the object because of the 2. That's the first thing. 1. I'm going to list them for you. 1. Sides on the image. That's under V, you know. Sides on the image are twice the sides on the object. Remember, the object is triangle ABC. So the size on the image is twice as long as the size on the object. That's on the transformation V. We're talking about what happens on the transformation V, where V is the enlargement up here. So the 2 cause this first. 2 cause that. The 2. What else does the 2 do? Secondly, the 2 pushes the image twice the distance from the center, where the center is the origin. So you're going to say not just, don't just say center. You know that the center is the origin. So say origin. Right? Say origin. So the image points are twice the distance from the center, which is the origin. So say origin, because you know it's the origin. So twice the distance from the origin. You know, so be specific. Be exact. Mathematics is an exact science. So the image points are twice the distance from the origin as the corresponding object points. right? So what I gave you on the must know sheet was just a short summary, an abbreviation, a little quick way to remember what happened. We don't have to be using and copying those exact words. Right? By copying those exact words, I don't know if you fully understand what happened. So if you understand what I'm writing now. So the sides are twice as long, right? And the points are twice the distance away from the center. That's what the 2 does. So far, we have always spoken about what the 2 does, the value 2. 2 causes them 2 things at all. And then now, the negative now is what does the inverting. And one person still wrote inverse. And I specified in the classroom that don't write inverse. It is inverted, like you flip it. You flip it over the center, which in this case is the origin. You flip it. All right. So the third thing what we're gonna write now is done by the negative. So let me put a little note. This is by this. This is by the 2. This is what is caused by the 2. This also is caused by the 2. I'm going to write what the negative does now. Taking my time, as we're moving on from this topic. 3. What does the negative do? The negative in the scale factor now. The image is inverted. The image is inverted. Flip it up. Flip it over. The image is inverted on the opposite side of the center, but you know that the center has the origin, so say origin, so it's of the origin. And when it's inverted, it will, and pointing, it will then point in the opposite direction. So the image is now inverted on the opposite side of the center, which is the origin, and pointing in the opposite direction. So the points are pointing in the opposite direction. Right? It is pointing in the opposite direction. So what the points on the object are now pointing in the opposite direction. This down here is what the negative does. This is what the negative does. This is done by the negative in the scale factor. So the 2 do them 2 things here, twice as large and twice the distance away, and then negative now in the scale factor inverted. If the negative was not there, then this third part would not happen. It would just be twice the distance away, right? And twice as large, and then it will be pointing in the same direction. But the negative now inverts it and points, have them pointing in opposite direction. So the image and the object are on opposite side of a center. And that is the description of what happens. But there's a 4th thing that happened that we can mention. That's not on the must know sheet. It's on the must know sheet indirectly. A 4th thing that happened, and that happened by the 2. So I mention it for good measure. Remember, we're going to use and mention that. Remember that area of image is k squared times area of object. The k is 2. So the area of the image is 2 squared times the area of the object. So the area of the image is 4 times the area of the object. And so we can say that as well. The area of the image, that's the image of triangle ABC. The area of the image is 4 times the area of the object, and the object, remember, is triangle ABC. Triangle ABC. So nobody did this. That's fine because it was not on the must-know sheet, but that's how I come to class. So that's another thing that happened. The area becomes 4 times what it was because it's 2 squared, K squared. So the area is now 4 times what it was. All right? That is part 2, guys. This is part 2. All right, come to part 3. Any questions there, but all right there so far? But okay?
Yes, sir.
Yes, sir.
Beautiful.
I have a question.
Yeah?
Sir, for that question, right? Suppose like they gave us a specific amount of marks, like 2 marks, so only have to write 2 or have to write all of them.
No, you don't know they're applying the marks in a boss. So you give them everything you know. Now remember what I said, you know. I was the person who put this question in there, you know. CSEC never originally put that in the question. So in this question, I think they said this in about the 1990 something. This was a question and they would ask these 3 things. I was the one who put this as a part of the question. Just because I wanted us to, you know, have a focus on how the scale factor works. So that's why I did that part and put that part in there. But this was not in the original question. So there was no mark for that. You understand me? I just put that in, as I said, just to you know, help us to learn more. All right. So the question really only had these 3 parts on the exam paper that I took it from. All right. So that is that. All right. So and generally speaking, students, don't watch marks when you're working question. Just answer them the best way. Just answer them the best way. I can tell you one reason why. Sometimes on the exam paper, you know, a question is listed as word. Let's say they give 1 mark on the question paper. Sometimes when they go to mark the paper, you know, right? The chief marker might say, no, that this question really value 3 marks. And they can change the mark scheme when they're marking it. So instead of giving 1 mark that you see on the exam paper, they might change it. And same way, they might have a question on a paper that they have as value 3 marks. And when the time to come to mark it, they might say the question on a value 3 marks, you know, because it's really very easy, you know. And they might change it to 1. Right? So don't watch the marks. Don't let the marks be the guide to what you do. Yes, sometimes you give a little indication here. Yes, but you will know still. But it don't matter. If a question value 1 mark, you want the 1 mark. If a question value 8 marks, you want all 8 marks. You must always want all the marks. Do everything right. You understand? On average on the exam paper, question value 2 marks, you know, on average, you know. Question don't really value, the question parts, and don't really value no big marks, you know. Most of the time is 1 mark, 2 marks, 3 marks. You hardly see a question value 4 marks and 5 marks. Hardly. They usually value some small marks. You understand? So you want the marks. Because if you keep giving up 1 year and say that only value 1 mark, that only value 1 mark, that only they add up. If you say that 5 times, 6 times, 7 times, 7 marks that they're giving up. So don't bypass a question because you see it's a small number of marks. And just do the question, just answer the question. You know, if you're well prepared, you'll know how to answer a question. That is why we have preparation. So you know exactly how much work to put in to a question. So, you know, don't watch the marks, just answer the question. All right, part 3. So part 3 says what to determine the 2 by 2 matrix. I think this was well answered. The persons who did this one, they did it well. V followed by W, right? And they wrote it out. V followed by W is, everybody knew it was WV. Some person might have made a mistake in actually doing the calculation, but the good thing is that everybody knew it was W times V. Second one times the first one. You apply the second one to the first one. So it's the W matrix, which is 0, 1, minus 1, 0, times the V matrix, which is minus 2, 0, 0, minus 2. I have to put them in a correct order, guys. You have to put this one in front and this one second. If you put this question, it kind of funny, because if you make a mistake and put them the other way around, minus 2, 0, 0, minus 2, and you put them this way, 0, 1, minus 1, 0. You're going to get the same answer as this, because it's peculiar, right? Peculiar, so you're going to get the same answer, but if you put them in the wrong order, even if you get the right answer, you're not going to get the marks. You have to put them in the correct order, right? You have to put the W1, you have to put the W matrix in front of the V matrix in that order. Put them in the correct order. You can't just randomly multiply. Remember, matrices multiplication is non-commutative, generally non-commutative. All right, and we'll proceed to multiply these now the normal way. Multiply them the normal way. So the rows of the first matrix times the column of the second matrix. And getting a 2 by 2 meters. Almost everybody who did this. I think everybody who did this got it right. I don't remember anybody who got it wrong. All right, so the first value here is this times this and this times this. All right, so that's going to come out to be 0. So 0. Right, 0. And generally speaking, if you have 0 there, you're going to have 0 down here as well on the other end of the diagonal. That's how these questions usually go. And then the value here now, this row and this column. And so it is 0 times 0 and 1 times negative 2. So you see that work out to negative 2. This is negative 2. Then this value down here is this row times this column. So it's negative 1 times negative 2, 0 times 0. The negative 1 times negative 2 is positive 2. So that's a positive 2 right here. And then this value down here now is this second row, this second column. So it's negative 1 times 0 and 0 times negative 2. So that is a 0, which we know it's supposed to be. That's a matrix. And then part 4 now. Part 4 says using the matrix in part 3, meaning using this matrix here, we are to determine the coordinates of the image of triangle ABC under the combined transformation. So we're going to use a combined matrix to do the calculation. All right. So some persons did it individually, like so. So they apply, for example, combined matrix 0, minus 2, 2, 0, and apply to A by itself, which was 1, 2, and I work it out to get A prime individually, like that. And they said this times this, and this times this. It's negative 4. Right? For the first value, 0 times 1 is 0, negative 2 times 2 is negative 4. So you get negative 4, and then you get this times this is 2, and this time this is 0. This is 2. So you know, so A prime is negative 4, 2. And then I go on and do another one for B. Right? But what you can also do, instead of doing it that way, which most people did, was to just do one calculation and use a matrix 0, minus 2, 2, 0, and apply it to the matrix for A, B, and C, and make it smaller. So 0, negative 2, 2, 0, and find that combined matrix A, B, and C. So I can put in the 3 matrices in one. So to put the A, which is 1, 2, the B, which is 1, 1, and the C, which is 2, 1. Right? So it's like you have 3 column matrices in one. And you're gonna get back now your A prime, B prime, C prime. Right? Again, I'm gonna get 3 matrices in one. So really and true is like you're doing this calculation first by itself. Same thing would have gotten up there. So you get those values, which would be -4, 2. And then you're doing the matrix next times this. So you're doing next to get here now. Right? So you get 0 times 1
Sir,
minus 2 times. Yes?
if the ABC where you have the prime them pan say, if you left out them the pan the exam, you lose marks.
No, not really. But generally speaking, don't penalize of something like that. But you still want to show that you understand what does that mean and put on the prime. In fact, maybe double prime you want to put on. Because it's 2 transformations. It's even double prime. But if you put prime, no problem. Because they didn't specify in the name. But you want to call it something different because it's not the same points, right? So the same thing
Yes,
to do
sir.
on the prime. All right, good. All right. So back to this. All right, so we're doing the matrix times this column now, right? So it is 0 times 1, which is 0, and minus 2 times 1, which is minus 2. So the top value is minus 2. And then we're doing this value down here now, which is same matrix, 2 times 1, which is 2, and 0 times 1, which is 0, which is 2. So down here is 2. And then for C now, we're doing the matrix times the C column. All right. So it is 0 times 2, which is 0, and minus 2 times 1 is minus 2. So this is minus 2. And then for here now, we're doing this times the column. Right. So it's 2 times 2, which is 4, and 0 times 1, which is 0. So it's a 4. 4. We can't leave this as the answer. Our question said coordinates, right? Coordinates. Once you write in coordinates, I have to use this now, write the coordinates. So write A prime or double prime, -4, 2, -4, 2, B prime, or I can write B double prime, it's -2, 2, and C prime, or I could write C double prime, it's -2, 4. And then these are your answers. All right, that's that. Good? Nice and easy. All right, cool. So we're going on to vectors now, guys. So it's another favorite topic of mine. I'll tell you why it's a favorite topic of mine. So I told you why transformation was a favorite. Transformation is a favorite because you can know the answers before you even do it. And the reason why vectors is a favorite is because I basically set questions asking the same thing all the time. You will set questions asking about parallel lines and collinear points for the most part. And some displacement vector, they don't ask a lot of different things in the vectors question. Not a lot of different things they need to know. You know, like in transformation, you have a lot of different things. But if you just know these things, then you can know the answer to a question before you ever do it. In vectors, at this level, they don't ask a lot of different things. They don't ask you to do a lot of different things in the vectors questions. Right? And another thing is that you have multiple ways to do each question, at least 2 ways most of the time to do each question. Right? But the thing about it, remember, you're preparing for an exam that you have to do all questions. So in the past, some students will say, boy, I'm not about to do vectors here, man. And they have a choice of maybe skipping over the vectors question in section 2, because there used to be a full vectors question in section 2. And there used to be like, I think, 4 questions, 5 questions to choose 2. That's in a long time past. And then now it used to be 3 questions to choose 2 in recent times, in the more recent past. But now you're doing an exam, you have to do all questions. So therefore, you have to learn all the topics. And I can tell you, there is no exam paper that don't have a vectors on it. None. Vectors must be on the exam paper. And it usually come as one of the last questions. Question 10, either question 10A or question 10B. And then you also have vectors all over the multiple choice. You get about 3 to 5 vectors question on the multiple choice out of the 6. All right, so you cannot avoid vectors. You must do vectors. All right, but believe me, it's nothing. I can tell you off the bat at this level, vectors really is about how you go from one point to another point. Right? So if I'm here and I can go there and I can go there, and I want to go here, but it's like I don't have any road here. I don't have any vector here. Then I have to go here first and then go here. And that is equivalent to going straight to there. So vectors really at this level, in a simplified way, is about how you go from point to point, going along vector direction that you know. All right, vector direction that you know. So let's look at the notes. Let's go through the notes. I think I want to break down the notes over 2 days. So do some of it today and do some of it tomorrow. All right, so let us go through the notes. All right, so it's vectors. We'll learn now. Vectors, our next topic. All right, so what's a vector? A vector is a quantity that has both magnitude and direction. What do we mean by magnitude and what do we mean by direction? So magnitude is size, and direction, as it says, is direction. Like you're going east, you're going west, you're going up, you're going down. Magnitude is size. So for example, I think we have some examples here. So a scalar quantity is one that has magnitude only. Scalar quantities are one that has magnitude only. So I'm going to compare vector and a vector quantity and a scalar quantity now. So let's take velocity versus speed. What's the difference between velocity and speed? Velocity is speed in a specified direction, while speed is just speed itself. So for example, take for example, like we're driving on the road. I know the police on the road, they usually have these speed guns that they use to measure how fast the car is going, right? So when they take the gun and they point it on the car and they shoot the radar onto the car, then the gun shows them how fast the car is going. So the gun is just giving them the speed, the raw speed, because it's called a speed gun. Now, if the gun was a velocity gun, what the velocity gun would do, it would give them the speed, but it would also specify the direction. So for example, if it's a speed gun, what would come up on the speed gun is something like, for example, 50 kilometers per hour. So the car is going at 50 kilometers per hour. If it was a velocity gun, the velocity gun would say the car is going at 50 kilometers per hour northeast. So in addition to giving the 50 kilometers per hour, it would also give the direction. So that's what vector is. A vector is a quantity. It has a size like the 50 kilometers per hour, but it also has the direction, right? That's just an example. Displacement versus distance. Displacement versus distance. Now, displacement is distance moved in a specified direction, while distance is just distance. Like you might say, all right, the distance from Kingston to Montego Bay. For argument's sake, I don't know the actual distance, but I'm just going to throw out a figure. Says 300 kilometers. Right? Says 300 kilometers between Kingston and Montego Bay. Just throwing out a figure. I don't know what it actually is. Right? I don't know. So the distance between two places, two towns, town A and town B. It's 300 kilometers. Then that is just a raw distance. Whether I measure it from town B to town A, I measure it from town A to town B. The distance is just 300 kilometers. If you're talking about displacement, you can say the displacement from town A to town B is 300 kilometers east. From town A to town B, the displacement is 300 kilometers east. Therefore, The displacement from town B now to town A will be 300 kilometers west.
Wait, excuse me, sir.
Yes.
Do each vector and scalar like have their own pair when it like velocity and displacement and
Where's a pair? I mean, what I mean by pair?
Like one shows the one shows the vector quantities and one only shows the scalar quantities. Right?
Yeah, man, a scalar. No, man, a scalar quantity like these, they just tell you the raw size. They don't mention nothing about direction. This one mention the direction. The vector quantity is one that gives the direction as well. So they give the size and the direction. That's why I spoke about R. Car could be going 50 kilometers. Yeah.
So I'm saying like if there's one, like if there's a vector quantity for every scalar quantity. That's what I mean by pair.
Oh, so you mean, yeah, man, because you can, anything that can be measured, you can turn it into a vector by specifying a direction. Good question. Yes. Anything that can be measured, generally speaking, any quantity that can be measured, right? Quantity that has to do, any quantity that can be measured. Yes.
So sir, do you have a vector and scalar for time?
All right. Good point.
Moment.
Good example. Good example. So, no, man. What she's basically saying is that time don't have no direction. Time don't have any direction. But listen, but time still can have a direction in a sense, because you can say a certain amount of time to come. I can say a certain amount of time passed. And in fact, sometimes we're doing some questions like in physics, and you're doing a calculation and the time come out negative. If the time come out negative, it means that it's time past. But if the time come out positive, it means that it is time to come. You understand the point? You understand what I'm saying? So you can
like
be doing
forward in time and backward in time?
Yeah, something like that. Like you're calculating the time, but the time that you calculate is time that has not passed as yet. It's time like 10 minutes from now. That's 10 minutes from now, something got forward. But you could be calculating time and the time come out to be 10 minutes, something happened 10 minutes before now. 10 minutes before now. So in a sense, there's like a vector component to it, but really and truly, time would be a quantity that you would say, all right, no, time not really have no vector quantity. But you would generally know things that can have a direction can have a vector component, or it can enter a scalar component. Things that can have direction. Things that can have direction. Right? So for example, mass. Take mass for example. Mass is something that you can measure, but mass don't have no direction. Mass is just mass. But weight is a vector quantity. Why? Because weight is usually something pulling you downwards, or weight is a downward vector. Weight tends to pull you downwards. So the direction of weight, generally speaking, is downwards towards the center of the earth. Right? Another one, I don't want to get too much into physics, but that's what it is. So mass don't have the direction. Mass is just a scalar quantity. So therefore, you guys are answering the question. Not all quantities not all quantities have vector components to it, because mass don't have no vector component to it. Mass is just mass. It don't have the direction. Same thing with volume. Volume don't have no direction. The volume of something don't have no direction. Right? So these vector quantities usually is in reference to motion. It's usually in reference to motion. Things that have to do with motion are the ones that can have vector, like displacement, velocity, acceleration. Those are components of motion, things that are moving. Also force has a direction, because it can be pushing or it can be pulling. So pulling is one direction, pushing is one direction, pulling is another direction. So you push with a certain amount of force, right? So pushing, the force that you push with is a vector quantity. Okay, you can be pushing something with a certain amount of force in a particular direction, and you can change the direction in which you are pushing that thing. So things that have to do with motion are the things that that usually will have a vector component and a scalar component. The scalar component is the magnitude of that quantity, while the vector component no is direction that you're applying that quantity in. All right, but they're not going to test all of that in the maths, you know. All I need to tell you is that most of the questions that you'll be doing will have to do with displacement. I think going to have to do with this one. How you go from one point to another point? How many units? So, and how many units? So, this way, and the resultant is this. Something like that. That's what most of the questions are about, getting from point to point. Most of the questions in vectors at this level is about how you go from point to point, going along vector direction that you know. We're going to see that in the questions. So make a move on. All right. So how do we represent vectors on paper? On paper, and you have to draw. You're going to give vector diagrams. They are represented with a line, a straight line, with an arrow on the line. That's how they represent vectors. The length of the line, the arrow on the line represents the direction, and the length of the line represents the magnitude. So for example, if I want to represent two cars driving on a road, right? And one of them going at 30 kilometers per hour, I can draw a 30 centimeters line, like so, 30. If I'm going to draw another car going at 60 kilometers per hour, but going in a different direction, then I would have to draw a line twice as long as that one. Twice as long as that one. So if this one is 30 kilometers per hour, and I want to represent one that is 60 kilometers per hour, but the direction might be different, then it has to be twice as long. So if this is 30 centimeters long, then it should have to be 60 centimeters long. So if 30 centimeters represent 30 kilometers per hour, then 60 centimeters must represent 60 kilometers per hour. So the length of the line is representative of the magnitude, and the arrow on the direction of the line is representing the direction. All right, and we'll see that. So that's how we normally represent a vector, a line with an arrow on it. And it's usually from a point to another point. We're going to be focusing on displacement vectors in this class, or at this level. Right? We could also have another one, PQ, another direction with the arrow on it. So when you're using the endpoints, the A and the B, for example, and the P and the Q, you put the arrow on top. That's how we do it. When you're using a common letter to represent the vector, you underline it. So you should underline the common letters when you use it to represent a vector. If you're using the capital letters at the endpoint, you put an arrow on top. Very important. This is very, very important. And that's how you represent a vector quantity. Because if I, for example, just write AB, if I just write AB, for example, AB now would mean the actual length of the line AB, while this means how do I go from A to B? That's what this means. This means how do I go from point A to point B, while this one down here means the length of AB. So to make the distinction, you put the arrow on top, the one that is talking about how you go from A to B. All right. Same thing with here. It's another example for PQ. Underline when it is represented by a common letter, you put the arrow on top when you're representing a vector with the common letters of the endpoints. And we're showing you the standard way to represent vectors, everything important, starting from the basics. So that's how we represent vectors, all right? Underline common letters, When you use the capital letters for the endpoints, you put the arrow on top. The arrow on top don't mean the length of a line. It means how you go from one end to the other end. So for example, in this diagram here, to go from A to B, I could say, okay, I go this way first and then go here. And therefore, I can express this in terms of this movement and that movement. So I can write it therefore as AB like this. She's telling me how many units to the right and how many units up. So it's sort of similar to translation. Similar to translation. All right, well, let's continue. So that is it. You underline the common letters and you place the arrow on above the capital letters when you're writing vectors. All right, resultant vector. That's a resultant vector. A resultant vector is one vector that can be used to represent the final outcome of more than one vector. All right, so that's it. A resultant vector is a single vector, one vector that produces the same result, the same outcome as more than one vector. It should be vector, more than one vector. Lots of this for that for me. All right, more than one vector. All right. So for example, now, so here now, we are now developing our vector equation. How do we read a vector equation? So getting into it gradually, you know, starting from the basics, or building up this vectors thing gradually. All right. Remember, you're not going to start to fully understand these things until we start doing questions, you know, but I'm building up gradually. So here now, we are starting now to develop our vector equation, how we read the vector equation, and what does the vector equation mean? That's what we're looking at right now. So consider 3 points on this diagram here, A, B, and C. To go from A to B, we could use the vector AB. Let's show that on the diagram. That's the vector AB, taking us from point A to point B. Then to go from B to C, we could use the vector BC. So we go from A to B, and then we go from B to C, using the vector BC. So where did we start? We started at A and we ended up at C. So those two would give us a resultant. AC will be the resultant of those two. So the vector AC is the resultant of those two, because going from A to B and then going from B to C is equivalent to going straight from A to C using the vector AC. And what it means then is that the vector AC is the resultant of the AB and the BC, and that gives us now our vector equation. So in this case, AC is a resultant of the AB and the BC, and therefore we have our vector equation. So let us talk about how you read this vector equation now.
Sir.
Yeah?
Is that something similar to Pythagoras theorem?
No, Pythagoras theorem is measurement of length. No, not similar to Pythagoras theorem. Just think of it as you saying, how do I go from A to C? To go from A to C, I can go A to B first, and then go from B to C. And that is how you actually read this vector equation that I have on the page right here now. This. That's how I wanted to read this vector equation. This.
Excuse me, sir.
This part is this, yes?
Sir, like where you say the vector moving from A to C, and the arrow is used to represent which direction it's going to. Does the two arrow stand there as a representation of the rest? Like where you have one, and but at AC you have two.
All right. So the AC, we usually put double arrows on the resultant vector. That's all. The resultant vector, I usually put double arrows on it. But if you even don't put the double arrow on it, no, it's not a problem. But generally speaking, they usually put the double arrow on the resultant. And that's why I put a different color for it as well. So it is a resultant. All right, so let's get back to this now. How do we read this vector equation? And I want us to read it the way I'm telling you. So a vector equation, let me finish the slide first. It's different from a scalar equation. That is it. We're not talking about length. It is obvious. It is obvious, guys. It is very obvious that this length is not equal to, right again. It is obvious that this length is not equal to this plus this, don't it? Agreed? This plus this must be longer than this. But agree with that? So there's no way
Yes,
this
sir.
equation could be saying that. There's no way that equation could be saying that. Right? So that's what this little note right here is talking about. In terms of length, we are not saying that AC is equal to A plus B. So this equation cannot be talking about length. And if you can understand that with vectors, then you're halfway to solving vectors. That's a mistake a lot of people make. They believe that this equation is talking about length. No, it's not talking about length. It's talking about displacement. How do you go from A to C? So let's say you read this equation now. To go from A to C is the same as, that's what equal mean in vectors. Equal in vectors mean is the same as. Is the same as. So this equal means is the same as. Is the same as. That's what equal mean in vectors. Going from A to B, the plus in vectors mean and then. And then. That's what the plus mean in vectors. So when you have a vector equation, equal means is the same as, and plus means and then. So that's why I want to read the vector equation. So this equation here now is read. Going from A to C is the same as going from A to B and then going from B to C. Makes better sense? Make better sense if you read it like that?
Yes, sir.
So even though mathematically, when you have figures and numbers to work with, you're still gonna use the plus as you do use the normal plus. And still gonna use the equal as you use the normal equal. In terms of saying it and in terms of what it represents, the equal means is the same as, and the plus means and then. Right? We're talking about the length, then we're talking about equal in the normal equal, and we're talking about plus mean addition, plus. But in vectors, the plus means and then, and the equal means is the same as. So that's how we're going to read our vector equations. So it's talking about how you get from one point to another point. To go from A to C is the same as going from A to B first, and then going from B to C. That's what vectors is about, and that's the basics of a vector equation. If you can understand this, yes.
So if you said like A to B, B to C, if them say from C to A, would it be plus or minus?
If we go C to A, we're gonna come to minus vectors just now. What the minus mean in vectors just now. Good question, and I like the forward thinking, but we're coming to it. We're building up little by little. We're gonna see what the minus in vectors mean just now. And the minus in vectors mean really going in the opposite direction. Minus in vectors mean opposite direction. We'll come into it. Just tell me if you understand what is on the page right now. So far.
Yes, sir.
All right, good.
Yes, Dad.
Beautiful. All right, good. So make a note of what I wrote here now. Make a note of what I have down here now. Make a note. Very important what I wrote down here. That the equal means is the same as, and the plus means and then. And you know that you have a vector equation because you have these arrows up here. Right? Look down here with no arrows on it. This is talking about length. That equation on this side is talking about the length. That's how I had to put not equal to. Because we're now talking about length. When you don't have the arrows on it, we're talking about the length of the lines. With the arrows on it, we're talking about the direction or displacement from A to B, from A to C is the same as going from A to B and then going from B to C. That's how we can get from A to C if we want. All right, so that's what vectors is about, how you get from a point to a point. Start out dealing with vectors that way, and you're on your way to doing vectors. All right, so you put a double arrow on the resultant. So you see it there? That's why I put a double arrow on the resultant. It's the standard way of representing the resultant with a double arrow. All right. Equal vectors. We're getting into the various things now. Equal vectors. So two vectors are equal once they have the same size and the same direction. two vectors are equal when they have the same size or the same length, same magnitude. Magnitude is another word for size. Modulus, magnitude, size mean the same thing. So magnitude, let me write over here instead. Magnitude, size, length, and one other word, modulus. Modulus. All of these mean the same thing. They're referring to the size of the vector, the magnitude of the vector. Magnitude, size, length, modulus mean the same thing. All right, talking about the scalar aspect of the vector, not the direction aspect of the vector. All right, so vectors that have the same size, magnitude, length, modulus, and also have the same direction are equal vectors. Same direction, same size, they are equal vectors. Let me show you how this is applicable now, right away off the bat. So for example, if you have a parallelogram, and CSEC like to give vectors questions with parallelogram. If you have a parallelogram like this, so I'm introducing it right away to parallelogram. Because CSEC like to say parallelogram vectors question. Enjoy it better. Parallelogram. But you know what a parallelogram is? There's two pairs of equal opposite parallel size. Parallelogram means that this side here and that side here, them equal in length and them parallel. And a side here and a side here, equal in length and then parallel. Watch this now. If the question tells you that this vector, this side is vector A, it automatically means that this side also is A. But they're not going to tell you, but you have to know. Why is that one equal to A? Because them parallel and them equal in length. If we put another line down here, parallel to that, and the same length, parallel to that, to those two, and the same length. Even though it's down here, it is still equal to vector A. So once the vectors, once the lines have the same length and the same direction, then they are the same vector, no matter where it is. Continuing, if this vector, this side is vector B, then automatically this side is vector B as well. Because these two sides have the same length and then parallel, same direction. And if I draw another line down here, all the way down here, I draw another line down here, horizontal like that, and the same length as these, same length, then this vector all the way down here is vector B as well. Even if it is on another diagram. Once they have the same magnitude and the same direction, they are the same vector, equal vector. But understand that? And CSEC like to give parallelogram questions. And when I give you the parallelogram question, I will give you this one and this one. You have to know that this one equals this one and this one equals that one. You have to know. You have to know because of this rule over here that we're looking at. Parallel vector, equal vectors. All right? So they don't have to be located at the same place. So that's why I said if you have one all the way down here, don't matter, it's still the same vector. If you have this A all the way down here, it's still equal to this and still equal to that. They don't have to be the same place. But understand that.
Yes,
Once
sir.
you have the same length and the same direction, they are the same vector. So if I have a vector right there, AB, and I have another vector PQ, same length, same direction, it means that the vector AB is equal to the vector PQ. So whatever AB is, PQ is the same thing. That's what it means. AB and PQ is the same. That's what it means. So if I call this AB vector, if I call this vector U, then this one is also U. So this is equal to U. That's it. Once them have the same magnitude and direction, they are equal. And that is equal vectors. We're gonna see a lot, we're gonna have to deal with a lot of equal vectors going forward. Because CSEC likes to give parallelograms. All right, let's continue. Building up slowly, slowly, giving all the foundation work first. Inverse vectors. Now, this is where we now introduce what the negative in vectors mean. The negative in vectors simply means opposite direction, basically. Think of it that way, opposite direction. That's what the negative does, reverses direction. So the same magnitude, parallel, but opposite direction. So these have equal magnitude, but opposite direction. That's inverse vectors. Equal magnitude, opposite direction. So just think of it as inverse. What does that inverse do? Reverse is what took place. We can look back over here again. So remember now, we're talking about a displacement, talking about mainly displacement. So if you have A up here and B up here, I have a vector taking you from A to B. What will take you back from B to A? The inverse. The inverse take you back. So the inverse of a vector is a vector the same size in the opposite direction. So it's similar to the inverse that we dealt with in functions, something that is taking you back. Inverse is transformation, something that is taking you back. Inverse in vector is the inverse that will take you back. So it's a similar sort of thing. But now, in terms of your, it's like the inverse translation that we did. Because you see the vectors that we're gonna do, the transformation that it is closest to is translation. I'm gonna see that. So the vectors and the translation kind of similar. So it's like the vectors is an extension of the translation and transformation for the most part. You can look at it that way. All right. So we'll see the connection between all these topics. All right. So if I have a vector that takes me from A to B, then the vector that takes me from B to A is the inverse. And your relationship is that a negative sign is introduced. So see the relationship that we end up with here now. So this goes for all vectors. All vectors. So simply means, look over here now. Vector PQ is equal to minus QP. Them two are the same, equal to that. The vector MN is equal to minus NM. And let me show you what I mean now. Suppose we have an equation, a vector equation that says, we have a vector equation that says AB say plus PB. AB plus PB. Watch this now. It's a plus PB, right, that I have right here. I can change the equation and write it as AB minus BP. Put another way. If this was a minus BP. This is a minus. This is a minus BP or PB. Yeah, put it that way. That was a minus. The minus in vectors mean that I can reverse the direction of this and change it to a plus. So it means that I could write AB plus, means that, and then BP. Why? Because the minus PB is the same as BP. The minus in vectors mean opposite direction. And then what does this mean? This means going from A to B and then going from B to P. And the final answer would therefore be AP. Because you go A to B and then B to P is the same as going straight from A to P. Right? Enjoy it for you. You go A to P and then you go P to B, A to B, and then you go B to P. Go A to P, A to B with that, and then you go B to P with this. And so the final answer is AP. AP. So the minus in vectors mean opposite direction, right? But don't worry, we want to see how it is used. Just know that the minus in vectors mean opposite direction. So on this diagram right here, let me show you something up here again. On this diagram up here, suppose I give these points letters. I'm going to show you. So I'm going taking your head, So I give these endpoints letters. So this is O and O, P, Q, R. Suppose I give those points letters. I can write this, watch this. I can write OP equals the vector A, But understand that? To go from O to P, I can use the vector A. I can write PQ equals the vector B, don't it? But I agree with that?
Yes, sir.
Yes, sir.
I can watch this now. What would QR be equal to? QR.
A.
QR.
Yeah,
Look at
equal to A,
QR now.
sir.
Huh?
No, negative A, sir.
Very good. Okay, going in the opposite direction to A. See? Remember, A is up this way, up. QR means that I want to go this way. So it will be negative. It will be negative A. See? Negative A. Because I'm going in the opposite direction to A.
That's supposed to be E or AP, the first
Huh?
one, sir. Is that AP is right or is
OP,
it
OP. So I change it to OP. OP. Change it to OP.
Question, sir.
Yeah.
Sir, like when you state that the arrow states what direction you're going in, right? And you said that here we're going in the opposite direction. So doesn't that mean
Which
the
one?
arrow
For this
change
one?
directions as well?
No, but if you know that this is A up here, that is A, then in other words, put it this way. Put it this way. If I am writing RQ, then RQ just be equal to A. RQ is A now. So RQ is A, because we know that this is A. That direction is A. That is what A is. So if you're going to go from Q to R, they're going in the opposite direction to A. So put the minus to show that they're going in the opposite direction to A. QR is minus A because it's the opposite direction to A. But RQ would just be A. RQ would just be A. Because A is given as this direction. A is given as that direction. You know that that is the vector A is given. Because they gave us this as the vector A. Therefore, this is also the vector A going up. So if you want a vector that's going to take you from Q to R, they're going minus A. They're going in the opposite direction to A. Same size, same but just opposite direction. The only thing different is the direction. So when the direction is opposite, you put the minus there to signify that you're going in the opposite direction. Understand?
Yes, sir.
So that's how the negative works in vectors. When you go in the opposite direction, you introduce the negative. All right? The negative in vectors means opposite direction. All right. So we're still building gradually. All right? Still building gradually. So BA is the inverse of AB because the direction is opposite. Same size, just the direction that is opposite. All right. Addition of vectors. How do we construct the addition of vectors? That's what this part is about. We're going to add vectors numerically soon. But how do we construct the addition of vectors? Remember that the plus in vectors means and then. So in order to constitute the and then, you have to keep the flow of the direction. Right? You have to keep the flow of the direction consistent. And that is why we add the tail of the nose of the vector. We add the vectors nose to tail. Tail of the second vector to the nose of the first vector. So that the direction remains consistent. All right, it's like a flow direction you're going. Because the plus in vectors mean and then, it means and then. So look at this example now. Suppose I have that vector U and I have another vector in another direction with a different magnitude, and that vector is V. And I want to construct the vector U plus V, U plus V. Remember that the plus means and then and then. This means and then. So it means that I have to put down the vector u and then put the vector v behind it so that the flow direction is consistent. So look at it. I can position a vector u, then I have to bring the tail of v and put it on the nose of u so the direction remains consistent. So see there? Like that. That is my u and then v right there. So now we know. So the resultant of my u and then v is that vector right there. So that would be a vector u plus v. That is u plus v, you know, the red one. But understand that? That
Yes,
is the
sir.
result of u and then v. So that's how we construct it from scratch. All right, beautiful. Let's do the converse now, or the minus. How do we subtract vectors? Remember, we don't have anything. We don't have anything that means. Huh? Listen, let me
Right, so I
explain.
can write the topic and part.
So you want to write off this?
I did. Yes, sir, I did almost finish.
All right. But why you writing it, man? You don't have the handout for it. It's in the handout, you know. It's in the handout. Everybody's supposed to have the handout.
Yes, sir.
It's in everything on the slide. Everything I put on the slide is on the handout, you know. The only thing that would be an handout is the and then that I put there. Right? All right. So let me continue.
Sir.
So, huh? Can I move on?
Yes, sir.
All right.
Yes, yes, sir.
So, I remember we do have the definition for the subtracting vectors, you know. We'll have a definition for the plus. The plus in vectors mean and then. So to subtract a vector, what we do, we add the inverse. Remember, the minus in vectors means inverse, you know. So you add the inverse instead. So look at it now. So to subtract a vector, we add the inverse. That's how we construct it. We're talking about construction. For calculating, we just subtract same way, no problem. So subtract the values. But we have to understand what it means in terms of diagram. It means you add the inverse. You see it here now? So if u again and v, and we want to do u minus v. So let me write it for you now. To do u minus v, we look at it as u and then minus v. So we look at it, you know, u and then minus v.
So, sir,
Yeah.
so basically, it's just the formula for addition, but one of the values is negative or both of the values negative.
Negative means instead of using the v, you're gonna use the inverse of v. What's the inverse of v? Inverse of v is just like a v in the opposite direction, you know. So like a reverse the arrow on the v. Let me show you on the slide. So u minus v is same as u and then the inverse of v. U and then the inverse of v. Right? So look how you construct it now. So I'm going to put in the inverse of v on the diagram now. Look. That's the inverse of v, you know. Same length as v, but in the opposite direction. So what it means, therefore, I am now doing this and then this. That's what I'm now doing. Right? That's what I'm now doing. So look at it. I'm doing u and then the inverse of v. That is it, you know. That is u minus v right there now. U and then minus v. That's my resultant. So that vector is u minus v up there. That's u minus v. If you're constructing. All right. I want you guys to go back and watch these videos over again and get it in your brain. All right.
Yeah.
It will all become clearer when they go through everything. Yes?
So we still for attach the nose to the tail.
Yeah, man, you still have to attach the nose to the tail. See? You still have to keep the flow. So what we're saying is that, remember, adding vectors is an and then business. So instead of trying to subtract, you add the inverse. That's what I did. I added the inverse. So I did a u and then, see, u and then minus v. And the minus v is the inverse of v. Remember this thing in there, so I mean and then. And then, so you still do the tail, nose to tail. And then, that's what the plus means, and then. Right? So you see, you have to keep the flow. See, you have to keep the flow this way. See that? You have to keep the flow. All right, you have to keep the flow. All right, so let's continue. Position vector now. So you're gonna see do a lot of questions. In fact, we're supposed to be familiar with the term position vector from the transformation. So the position vector of a point is just how you go from the origin to the point. That's what position vector means. How is the point positioned relative to the origin? And usually position vector comes into play when you're doing the coordinate geometry aspect of vectors. When you put in the vectors on graph paper. But also it can be on plane diagram students. For example, in this diagram over here, let me use a different color. This vector will be the position vector of P, because we go from the origin to P. And this vector will be position vector of R, because we go from the origin to R. So position vector is the vector that takes you from the origin to a point, right? It's the smallest unit of vector. It's very, very important. All right, it's very, very important, and we'll see that as we go on. I don't want to talk too much about it yet. So position vector of a point, xy, is the displacement vector from the origin to the point. So basically, it's how you go from the origin to a point. And the beauty about position vector is that it will carry the same values as the coordinates, just as we saw in transformation. It carries the same values as the point, and that is how we write it. So you write OP, you put the arrow on top, the O on the P, and you write the points in a column vector form, just as we did when we're doing the calculation in transformation. Same thing. So we're seeing the connection now. Another way of writing it is that way, but I doubt you're gonna see that way in the exam. You're more than likely 99.99999% chance. This is what you'll see. This is for odd maths and pure maths. So this is what you will see. Now, almost all the questions we'll do, we're going to be using this format. All right, that is just for information. I'm not going to bother to explain the I and the J right now, right? Because we're just starting. They mean something, but I'm not going to bother with it right now. So the diagram here now is showing the position vector of P. Look at the diagram. See there? That's the position vector of P. The vector that takes you from O to P. But what you do, you express it in terms of the components, the X and the Y component. That's what you do. So if there's a point 34, A34, then the position vector of that point is written like that. You use the same values. OA34. What that means, let me show you what it means on the diagram. This point is 34. It means to go from O to P, you got 3 units this way, and then 4 units up that way. That's what the 34 means. To go from O to A, you displace 3 units to the right, 4 units upwards. So you see it's sort of similar to your translation. Similar to your translation. So the point is B -5, 7. Then the position vector of B is -5, 7. And the halves that in CXC, the actual question like that in CXC. So for example, in CXC, actual question I'm talking about now, they tell you that the point Q is 3, 8. And ask for the position vector of Q. And the answer is simply OQ equals 3, 8. Simple as that.
So
I've seen question. Yeah.
Has there ever been a question on the exam which incorporates many different topics under one thing, like vectors and matrices? Like they tell you to do this vector and then do a transformation with it.
No, not really. Not vectors and things, because It's because them said transformation. They tend to pair the transformation with the matrices. Because we notice that we use a lot of transformation. We use a lot of matrices in the transformation questions, right? So when they want to test your ability to do transformation and the matrices, they can put those questions together. But for vectors, no, because they don't tend to pair the matrices per se with the vectors. No, not with the vectors.
Yes,
All right,
sir.
not with the vectors. All right. So as I'm saying now, I've seen questions where they give a vector like this. They give a vector like this. They say the vector OA is equal to 5, -4. And they ask a question like, what is this thing called? They ask a question like that, you know, what is that thing? What is the name used to describe this thing? What would you say? What is that thing? OA.
Sir, the
Random.
position vector.
Position vector of A. That is the question is, what is this thing called? They ask question like that, you know, we're gonna see it, you know, we're gonna see it. I think I did it twice. That thing is called the position vector of A. And if I ask for the coordinates of A, so they ask for the coordinates of A now, what would you say? That is the position vector of A. And if I ask for the coordinates of A, what would it be?
Sir, 5, -4.
Right?
Negative
Coordinates
4.
of the coordinates of A. Coordinates of A is 5, -4. So they actually ask that. So sometimes they give you a point and they ask you for the position vector. And they don't ask that, you know. So for example, the question will say, the point R is 8 - 5. And question is, what is the position vector of R? In words. Question is, what is the position vector of R? And the answer, so this is a part 1 in the question. The answer is OR and is 8, -5. And they actually ask that 3 marks that, you know, they ask that in question. We're gonna see it later. We're gonna see it. All right. So they ask for the position vector of a point and I give you the point is this. So suppose I say in a question, I say, I'll give you a question, I'm gonna talk about a point M, and the question say, what is the position vector of M? What am I asking you for? If I ask you for the position vector of M, what am I asking you for? If I'm doing a question,
Coordinates.
no, if I ask you for the position vector of M, I'm asking you for OM. If the question says find the position vector of M, I am asking you for OM. Question says find the position vector of P, I'm asking you for OP. Question says find the position vector of Q, I'm asking you for OQ. Position vector of a point is the displacement from the origin to the point. Yes?
Oh, I lose the penny.
Yeah, that's how you do it. Because the O is the origin. The position vector. Look at it now. Look what we're saying now. The position vector of a point, the displacement from the origin to the point. From the origin to the point. So once it says position vector, you have to put the O in front. Position vector of B is OB. Position vector of Q is OQ. Position vector of N is ON. Position vector of L is OL. Position vector of K is OK. Understand? That's the position vector mean. From the origin to the point. All right. Everything important. We're not taking anything for granted. So we understand what position vector mean. All right. Another term you'll see now in vectors is displacement vector. So displacement vector is when you're talking about between 2 points. So like for example, the displacement vector from between A and B is the vector AB. That's it. The displacement vector AB is a vector from A to B. from the point A to the point B. In other words, how do we go from point A to point B? Let's look at it. So we have this diagram, and those are the two vectors you know. So you know that this vector, for example, is OA. I know that this vector is OB. And you want to go from A to B. You really want to go from here to here. But you don't have no vector in those directions. What you can do, you can use a different color. You can come down to O first and then go from O to B. So what you have done, you have gone this way, which is minus OA. You're going up. You go opposite direction, and then you go OB. OB. Let's look at it. All right. That's what we want. AB. So to go from A to B, because you don't have the vector AB straight, you have to use up the vector direction that you know, which is the OA and the OB. So see it here now. We go O to A, we go A to O first, and then go from A to B, O to B. Remember we said the vector equation is saying how you go from point to point, right? So to go from A to B is the same as going from A to O first, and then going from O to B. That's what the vector equation is saying. Because that's what you'd have to do physically on the graph. But remember now, if you're using the inverse vector, remember what we said? This and this is the same. So the OA, we can write it as minus. The AO, we can write it as minus OA. That's what it is, you know, okay? You go in the opposite directions. So if you come down here, you go in the opposite direction. So that will be minus OA. And then you go up here, which will be a OB. That's what that is. I'm developing a very important formula for you. And that is what we say. So AB is equal to OB minus OA. We call it O times the last minus O times the first. Look at the details. Look at the details. That is a very important formula for you now. So the vector AB is O times the last minus O times the first. Things in maths have a last minus first kind of relationship, if you notice. Remember with the function with the f of g. F of g meant g followed by f. Remember? Remember it means you do g first and you do f. And with the transformation, for example, we did the v followed by w. Remember what the v followed by w was wv? See that? V followed by w was wv. W times v. The last one coming in front. You see that? Mathematics have this kind of reverse relationship, kind of like. And you can see it, and you can see the connection, right? But the vector AB, displacement vector AB, is O times the last minus O times the first. O times the last minus O times the first. I'm going to do some examples over here, so now. Everything important. So if I want the vector PQ, the PQ equal to, in terms of the position vectors. Displacement vector PQ in terms of position vectors is equal to what? Let me tell you the first one. OQ minus OP. O times the last minus O times the first. This is the last, this is the first. O times the last minus O times the first. Tell me the next one now, MN. Where MN equal to. Unmute the mic and tell me where MN equal to. Vector MN. If I want to find the vector MN and I know the ON and I know the OM, I know the two of them. How do I find the MN? What do I do?
Sir, O times the N minus
ON. Just a ON minus OM.
OM.
Good. Tell me now, RS. Where the vector RS equal to? Tell me.
Sir, OS.
OS minus OR. Come on, use the same language, man. Use the same language, man. Minus OS minus OR. Right? LT. The vector LT equal.
TS
O times
minus
minus
O times the
OT.
last minus O times the first. O times the last one. This is the last one. O times the last one minus O times the first one. O times the last minus O times the first. So it's OT minus OL.
minus OL.
Good? What I say that?
Yes, sir.
What are the letter we
Yes,
have?
sir.
Which letter I'm
Yes,
gonna
sir.
use it? I'm gonna use D and can't remember by letter E yet. I'm gonna use D and E yet. Where DE equal vector DE. Where D?
OE minus OD.
Minus OD. Very good. O times the last minus O times the first. Do another example. MQ. What the vector MQ equal?
OQ minus OM.
Minus OM. Beautiful. All right. RW. RW equal. Vector RW.
OW minus OR.
OW minus OR. That's how we find displacement vector, guys. You know why? Because we would know these. We would know those. So if you know the position vector of W and you know the position vector of R and you want to find the displacement vector RW, then it's O times the last minus O times the first. O times the last minus O times the first. Last minus first. O times the last minus O times the first. O times the last minus O times the first. So the vector ZR is equal to OR minus OZ. O times the last minus O times the first. O times the last minus O times the first. Because most of the times you will know these. You will know these. All right. And what we're going to do from this formula as well, we're going to learn how to transpose this formula. Transpose this formula. Because let me show what I mean by transposing this formula now. Suppose we have a vector. Suppose we have a vector equation PQ equals OQ minus OP. Suppose this OQ, me I try to find. I'm gonna know them two here. I'm gonna know this and this. I'm just transpose it. So it means the OQ. Instead of OQ, I don't know OQ would be equal to PQ plus OP. Carry the OP over here and add it. Simple as that. So based on this, I can make this a subject if I want, and I can make this a subject if I want. But this is where I always start. All right. So I can transpose this formula to make any one of them the subject. But just remember, basically a displacement vector is O times the last minus O times the first. And then I can transpose it to find any of the position vectors that I don't know. I will see that later. All right. O times the last minus O times the first. I could do it with some values now. So this is some calculation values now. So I have these two vectors over here. OA is 3, 4, and OB is 5, negative 5, 7. And I want to find a displacement vector AB. You see there is OB minus OA now. See there, this one is OB minus this one is OA. So this vector right here is my AB. That's my AB right there. But I see that? And you do the numbers normally. You do the numbers normally. You do the numbers normally. Right? So you see, it is negative 5 minus 3 is negative 8. Right? And 7 minus 4 is 3. All right, so I'm gonna put this into perspective here now. Now, what this means, guys, what this means is that to go from A to B, you got 8 units to the left and 3 units up. That's what that means, you know. So if I have to draw it, to draw what that means, it means that if we have the point A right here, so I'm going to go to B. This, remember, I'm going to go to AB. equals negative 8, 3 now. What that means is that to go from A to B, I have to go 8 units to the left. 1, 2, 3, 4, 5, 6, 7, 8 units to the left. This is 8 units to the left. And 3 units up. 1, 2 tall. 1, 2, 3 units up. So it means that B is right here. Yeah, 3 units up. So I've got 8 units to the left and 3 units up. It means that this is my vector AB right here. So the vector AB here, so that is my vector AB. That's what this means. It means to go from A to B, I got 8 units to the left and 3 units up. Straight line between A and B is my vector AB, broken down into 8 units to the left, 3 units up, just like translation. Just like translation. But understand that?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
So that tells me now, what that is telling us now is that when you do a vectors question and you have a diagram and you're also doing calculation, anything you get via calculation must match what you get on your diagram, just like how we did it in transformation, but even more in vectors. So when you're doing a vectors question and you get your answers, you can always check back the diagram to see if what your calculation is showing you is matching what the diagram is showing. And when we start the questions, I'm going to show you, but I'm just telling you that from now. What you get by calculation down here must match anything you have on a diagram if you are also working with a diagram. Because when you're doing the vectors question, there are some questions that you will get that is just pure calculation. And there's some question that you'll get that is just pure diagram. And there's some question that you'll get that have a diagram and calculation combination. So we're doing the diagram calculation combination questions. Anything your calculation give you, you can always check to see if the diagram match. If the diagram is matching what the calculation is showing you. And you'll know that your answer is correct if the diagram is matching. And sometimes you can use the diagram to solve it, or you can use a calculation to solve it, or vice versa. At the end of the day, what the diagram is showing you and what the calculation is telling you must match. Must match. All right? And that's why I want you to understand that a vector, displacement vector, for example, AB, negative 8, 3 means to go from A to B, you go negative 8, that's 8 to the left, and 3 upwards, just like your translation. So you see the relationship now between your vectors and your translation. You see the relationship. All right, let's continue. Let's continue. Still building up gradually. Building up gradually. All right, building up gradually. All right. Now we can also have a displacement vector. We use a different reference point other than O. Most times it's O you'll have, but the reason I'm putting this slide in is that sometimes they might give you a question where they don't give you no O. It's very simple. Just like how you would say O times the last minus O times the first. You just say point times the last minus point times the first. So that reference point is P. It's come back to the same thing. Look at it. Same thing basically. You're treating the point as if you're treating the O as if it was an O. You see it there? Point times the last minus point times the first. So if this basically, if I have the vector RS and my reference point is P, then it's P times the last minus P times the first. If my reference point is Q, then it is Q times the last minus Q times the first. If my reference point is M, then it's M times the last minus M times the first. Get the picture? If my reference point is L, then it's L times the last minus L times the first. But understand that.
Yes,
So I can
sir.
use any reference point if I don't have an origin O. Most times it is a position vector that you will have with the O. But even if you don't have an O reference point, you can use another point as a reference point. And just the last minus first, just the same. So just like how you can say O times the last minus O times the first. You can use any other reference point times the last minus the same reference point times the first. And the reason I put this slide on it is because I've seen questions that they don't give any origin point and students run into problems because they're so used to the O times the last minus O times the first, and when them don't see no O, they get confused. No, you can use any point as a reference point. It doesn't have to be an origin point. You understand? You can use any point as a reference point. And therefore, I could have this diagram and I have my y-axis and my x-axis here. Then I have my y-axis here, so my x-axis there, so I have my x-axis, I have my origin here, so. So these vectors are not in relation to my origin. They are in relation to another point P. I can still do my P times the last minus P times the first to get this displacement vector. All right, that's what this is all about. All right, so this guy is still last minus first. Same calculation again, see? So PA is 3, 4, and PB is minus 5, 7. I want to find AB, then it's PB minus PA, just the same. P times the last minus P times the first. So you get the same thing. All right, so I just put that in there. Addition and calculation now. Addition calculation. So this is just to show you that when you're doing your addition, even though you mean and then, when you're doing your addition, the mathematics comes back to your normal addition and subtraction that you do in mathematics. So even though you're doing vectors and nose to tail, so happens that your normal addition with the values, as we just saw a while ago, comes back in the normal way. So there's no special consideration when you're doing addition with the number, but the diagram will still match what the calculation is giving you. So let me show you with this example now. Bam. So let's have those 2 points, P and Q. All right. So P is a point 1, 3, and Q is a point 2, 1. Everybody can see that on the diagram? Everybody can see that, right?
Yes, sir.
Yes, sir.
Good. And another point O, and therefore I have those position vectors. So OP is a blue position vector, and OQ is a red position vector. Now I can add these two vectors, nose to tail, just the same way. I can still do my nose to tail with them. So if I'm doing OP plus OQ, then that will be my calculation. But I say that. So if I add the vector OP and the vector OQ, so this one goes here, and this one goes there. Then I add the values. 1 and 2 is 3, 3 and 1 is 4. So I'm adding my vectors. So that is telling me that when I add the two vectors, OP and OQ, nose to tail, this means OP and then OQ. My result is 3, 4. That's what that is saying, you know. My result is 3, 4. So look at it now. Look at the diagram. I'm going to add them. Remember though as well that I could have gone OQ plus OP is the same result mathematically, because remember 2 plus 3 is the same as 3 plus 2. So I'm showing that the mathematics work the same way with the vectors. So I can add them the other way around as well. And the diagram is going to show me that that is true. So in the case of OP plus OQ, I'm taking the tail of OQ and putting tail of OQ and put it on the nose of OP. Look at the diagram. That's it. Same vector that, you know, because I move the tail of the second vector and put on the nose of the first vector. I could also switch them around to match this calculation that I did down here, this one down here. Where I'm now putting the tail of the OP onto the nose of the OQ. Like that. You see that the end result is the same point. They meet at the same point. And if you look at the diagram, you see that that point up there, which I'm going to give it as that vector now, that's the resultant of those two. Look at it, you know, it's a resultant of those two. And anyone want to look at it, you know. So if I look at it as OP up here, and then OQ, up here. Then the resultant is this vector through the middle, which I've marked as OR. I've marked as OR. If I look at it the other way, then is the OQ down here first, and then the OP up here. Same thing. Come here and then go here is the same as going straight across here. So again, the result is still that point OR.
Sir,
Sir, can hear.
Buddy, can you hear me? Buddy back with me?
Yes, sir.
Yes, sir.
All right, cool.
Yes, sir.
All right, that's a little blip, right? So I'm saying that what we did by calculation here is matching what the diagram is showing us, and we can see it. We can see it. The calculation is telling us that our result is going to be a vector OR, which is 3, 4. And see it here? OR is actually at this point where the x value is 3 and the y value is 4, right? And so it concludes that R is a 0.34. So it concludes, the conclusion is that the resultant point is 3,4. So this is just to show you that what your calculation gives you and what the diagram gives you must match. And that when you're adding, you still add the nose to tail. Even if you do the nose to tail on the construction, the mathematics is giving you the same result. So whatever you get on the diagram must match what you get by calculation. So you must always look out for that. Always look out for that. And that your addition, you add the values the same way, the normal way. It works out itself. All right. So there's nothing special about the addition. Modulus of a vector. Modulus of a vector is just its length or the size. I told you that earlier. Modulus of a vector. We're looking at some other little components now. Right? Modulus, magnitude, length, size mean the same thing. In other words, how long is the vector? So when you're doing your questions, it's basically how long is that line representing your vector. And you basically can use Pythagoras system to work it out. So if I look at the AB as that amount of units to the right and that amount of units up, as it can be, the vector can be expressed like that, you know. If the V is AB, that's what it means. A units to the right and B units upwards to go from the tail to the nose. That's what the vector is. And I want to find the length of the vector. The modulus is the length of the vector. Then I will use Pythagoras' theorem. And so it will be equal to the square root of the A squared and the B squared. And this is a must know formula for modulus. This is a must know formula, guys. This is a must know. You must know that formula to find modulus or the length of a vector. All right, they don't ask a lot of questions with length at this level. They don't ask it all the time. But a few times they ask it, you need to get it right. The length of a vector is simply equal to the square root of the one coordinate squared plus the other coordinate squared. All right, simple as that. So you must know that formula. So if the vector is PQ, -3, -4, And the question asks for the modulus of PQ or the magnitude of PQ or the length of PQ or the size of PQ. The calculation is very simple. Square root of the first value squared and the second value squared, and its length, and modulus is written with this symbol on it. These lines. Modulus. And when you write the modulus, you can actually now write it just as PQ without the arrow, equal that. PQ without the arrow means the same thing without the arrow. The length of the vector, right? The modulus of the vector. That's why you write modulus with the two lines to the side, talking about the length of the vector. And it's Pythagoras' theorem we use. Right? I know we don't know the Pythagoras' theorem on that topic yet, but that's how it is sometimes. You have to use something before you actually learn it the formal way. But that's what it is. That's why sometimes you have to complete the syllabus and then revise. All right, so we can see the full picture. All right. So that's how we calculate the length of the modulus of a vector. It's something that CSEC asks all the time. Length of the magnitude of a vector. And just this formula you have to remember. Just remember this formula right here. All right, to find the modulus. All right, we're gonna see those in examples. These I'm gonna skip over these. This is not so relevant. I'm gonna skip over some things that are not so relevant right now. Slope of a vector, angle of a vector makes the positive x direction. I'm gonna skip over that. Portion vector of the midpoint. This is something that I needed to remember, guys, and pay attention to the details of this, because it's something that I find even some teachers made a mistake of teaching the wrong thing. They don't specify exactly what they're talking about, and students get the wrong idea. We're talking about the position vector of the midpoint of a line segment. Position vector of a line segment. Position vector, remember, means from the origin to the point. All right. So if you look at this diagram with the line AB, and I want the position vector of that point M in the middle, halfway point between A and B. So I'm talking about that vector from O to M. How do I find the vector OM if I know the vector OA and I also know the vector OB? So if I know the position vector of this point, meaning I know this, and I also know the position vector of this point, meaning I know that, how do I use these two to find this vector up here? Position vector in the middle, position vector of M. How do I use them? I'm just going to show the formula. I'm not going to prove it. It come like how you find midpoint in a normal average point, average of the x, average of the y. In this case, it becomes the average of the position vectors, the average of the two position vectors, the average of this position vector and this position vector. That gives you that position vector. Average, just like how you find the midpoint, average of the x, average of the y. With the coordinate geometry, that's how we find midpoint. Average of the x, average of the y. Notice average of the two position vectors. See there? Average of the two position vectors. OA plus OB over 2. Half of OA plus OB. That's what gives you the position vector. Common mistake for persons to do is to write that. And so OM is half of AB. Look here on the diagram. Half of AB is this. This is half of AB. That is what half of AB is. And that half of AB, if you notice, is AM. That is AM. I'm not asking you for AM, I'm asking you for OM. That different thing. I'm asking you for OM. All right, so don't give me half of AB as OM. That is wrong. That is wrong. But that is a common mistake people make right here. This right here is a common mistake that people make. And I don't want us to make that mistake. All right? This right here is a common mistake. I don't want us to make that mistake if I'm asking for the position vector of the midpoint. Just treat it just like how we did coordinate geometry, average point. Average of the position vector of A and B. Average. All right, so if I have those two, let me just write this one over here on the right. Let me write it over here. Just illustrate. So if I'm doing this one, I have OA is 3,5, and I have OB is minus 5, 7. And I want to find the position vector of the midpoint of AB. Midpoint of AB is M. Position vector of M is OM is equal to half of the OA and the OB, plus, not minus, plus, because it's average you're taking. So it becomes half of the OA is 3.5 and the OB is minus 5.7. Good. It becomes half of, no, this and this is minus 2. So yeah, minus 2. This and this is 12. 12. We take half of that here, minus 1, 6. So it means that the vector OM is minus 1, 6. Notice M is going to be the point minus 1, 6. Let me show you now the other way from our normal mathematics that the M will be minus 1, 6. Because what it means is that the A point would still be 3.5 if it's coordinate geometry, and the B point would be negative 5, 7 if we're doing coordinate geometry. And if M is a midpoint, then M will be equal to average of the X values. Remember, average of the X values, which will be 3 minus 5 over 2, average of the Y values, which will be 5 and 7 over 2. So you see that M would be the point. This will give you the negative 1 just the same. And this will give you the 12 over 2 is 6 just the same. So you see you get the same coordinates. But when you're doing the vectors, this is what you do to calculate the same average business. And you get this as a position vector with the point. So it's a common mistake people do, guys. I don't want us to make that mistake. This common mistake. I don't want us to make that mistake. All right, don't do that. Put as an X. Don't do that. All right, so this is another must know, guys. This is another must know. A lot of time they give you a vectors question and they ask about the position vector, the midpoint. I always like to talk about midpoint in vectors. All right, so this basically is the same calculation. We're getting the same negative 1, 6. And that is the point. The midpoint is negative 1, 6. All right. That's a point I'm going to stop today and pick it up back tomorrow. Let me see. Parallel vectors. Let me see. I think I'm going to pick it up back at parallel vectors tomorrow. Let me see what is coming up. Yeah, let me pick this up at parallel vectors tomorrow. Parallel vectors and collinear points. So I'm going to stop it here today. We're not going to do unit vectors yet, but I don't really set unit vectors questions so much. I'm going to do that unit vectors after we learn some stuff. All right, so yeah, so we're gonna stop it there for today and pick it up back at parallel vectors tomorrow. So what I want you guys to do for today, guys, is just let me tell you, most of the questions that we're gonna get, most of the questions will be centered around these parallel vectors. Most of the questions are gonna be centered around parallel vectors, using parallel vectors. So that's why I want to start with that fresh tomorrow. Parallel vectors and collinear points. Most of the questions will have to do with that. Parallel vectors and collinear points. So we'll deal with those tomorrow. And we should be able to do some questions tomorrow as well. And then on, I think we're gonna do a class activity on Wednesday. I think we're actually doing a classwork for this topic. Sunday, we're gonna do a lot of questions and give you a classwork on Sunday. So next week Sunday is gonna be a classwork day on this topic. So we're gonna be doing a lot of collinear points and parallel vectors. All right, so I'm gonna stop it there for today and pick it up back at parallel vectors tomorrow. I don't want to give us too many things. I want you to watch over the video. Don't want you to do any questions yet. Just watch over the video, right? Watch over the video. Transmit information that I gave you so far, and I'll pick it up back tomorrow. As I said, I'm starting back tomorrow at the parallel vectors, and I explain all these collinear points. I'm not going to use unit vectors yet. I'll unit vectors after we learn everything that they mostly said. They don't really set unit vectors questions.
Excuse me, Dad.
Yeah.
You said that there was going to be a must-know sheet like there was for matrices,
Yeah.
and
But
is there gonna
I'm not ready. I'm not ready for it. I'm not ready for you to focus on it yet. I'm not ready for you to focus on it. I still want to show you some other stuff first, because the main things that you're gonna be tested on in vectors, we're just gonna start it tomorrow. The main things. So far, what I've shown you, they don't really ask a lot of the questions are not centered around those things. What we're gonna do next, tomorrow, the parallel vectors and the collinear points, is what the majority of the questions will be centered around. The majority of the questions will be centered around those things. Before we go, I can just make it, maybe just have a quick look at a question paper, just to get a feel. So let me just show you what I'm talking about. I look at that question paper too. Let me just show you. No, not that, not that, not that, not that. So paper 2. So if we look at, for example, 2019, let's see what they asked in 2019 in vectors. Let me show you what I mean. I'm not gonna do any questions, it's not showing you how the questions are worded, what they tend to focus on. Let me show you. It's usually way down at the back. Last question. So you see, that's a vectors question. Very easy. And see, give it that diagram, and they're asking it for the vector AB. So they give it, the position vector of that, this position vector as well. They ask for AB, which is just OB minus OA. Right? You can work it out fast, right? Work that out. Then I ask for OD, which basically is this point. This point, OD. I'm going to show you how to find OD, having known this one. I'll show you that tomorrow. What is the ask you? BE. We go from B to E as this vector right here. You find BE. Come down here and then go there. Right, so you see it's very easy, trust me. And that's that done. Simple as that. That's that done. So not a lot of work. They're very easy. Look at another people. Look at another people. So about 2018 June. So I'm sure that it's very easy stuff. So feel what they ask. Very easy. Another one here. So you give a diagram again. Right. And they ask so complete the statement. What's the relationship between AB? Use this. AB and BC. See? They are parallel. And then they talk about the magnitude, which we're going to talk about as well. Express BC in terms of M and N. BC is this vector now, this vector. They're asking for BC. That's so to get to BC, you just come here, go down here, and then go there. And you add them up and get it. It's BC. Very easy, believe me. Very easy. And let's say midpoint come in here now. See, L is the midpoint of CD. Must find BL. So if you look at the diagram, L is the midpoint of CD. See, they put on it. L is right there. And I wanted to find BL. So BL is where you go from B to L right here. Where you go from B to L. Easy. come here, go here, and then go there. You're using those vectors. Very easy, trust me. Let's look at another one still again. Let's look at another one quick. This is 2017. It's got 2017, what I said. We're gonna work all these questions, right? We're gonna work all of them. That is showing you that the questions really short and spicy these days and very easy. The older ones tend to have more work. So here they give you a diagram again. And they give you these vectors, OP and OQ. They give you the position vectors there. They ask for OS. They tell you give you some information about the point S. We're gonna show you how you break down this information. Right? And they ask for OS. So that's this vector they're asking for. Easy, very easy. You're gonna see it. And PQ. PQ is this vector right here. Let's come here some and then go there some. PQ. They ask some relations. They ask for RS. RS. The diagram RS is this vector. So let's come down here some and then go there some to get from R to S. You know, so the question nowadays is even easier. Let me look at the older question. Not a long time one. The recent ones really very easy. Let's look at 2012. Let's look at 2012. It's 2012. So the marks in 2012. The older ones tend to be more wordy than this one. So they give you these position vectors. 2012, they give you these position vectors, three of them. They ask for BA, easy. This is just OA minus OB. See, O times the last minus O times the first. Then they ask for BC. BC is just OC minus OB. Yeah, they subtract the corresponding one. State one geometric relations with you. I'm going to tell you how you decipher this. Sketch them. I'm show you can sketch them as well. That's it on vectors. Easy. Easy. We can look at a January paper. January. So these are June. Let's look at a January paper. Show you January. Let's look at that. No, not that. Let's look at 2020. Zero. No, 2020. Let me show the marks in 2020. Always like the last question, the vectors. And sometimes you set out like the easy vectors in section 1 to win. So it's like transformation, you can get 2 vectors question as well. And so here the material must show something. Let me see what they gave in this one. Give a diagram again. It's a parallelogram now. So this vector over here is U. And automatically, this vector also is U over here. This vector down here is V. And automatically up here, so is also V. And then say now QM, MS is 1 to 2. So this is 1 part, 2 parts. So it means that QM is 1/3 of the whole line. And MS is 2/3 of the whole line. And so I'm going to show you how you deal with all of those things. As for QM. So QM is just this vector right here. So first question asks for QS. QS. First question is asking us for QS right here. So what do we go from Q to S? Come down here so and then go there so. Or from Q to S, you can come here so and then go down there so. You can go so and then go so. I'm gonna see them. Very easy. Very easy. All right. So I'm gonna show that. Say bring a midpoint again. I like to talk about midpoint, right? Who that the points are collinear? R, M, and T are collinear. T is the midpoint of PQ. So T is the midpoint of PQ. So T is right here. T's right here. I don't want to show that these 3 points are on a straight line. I'm going to show you how you do that by calculation. Show that those 3 points are on a straight line. All right, so we'll see. That's it, guys. We're going to stop it here today. Most of the questions have to do with parallel vectors, collinear points, and that's what we're going to deal with tomorrow. So basically, we're going to do the main things in vectors tomorrow. The main things we're going to do tomorrow. The main things is what we're going to do tomorrow. Anybody have any question? But all right?
All right, sir.
All right, sir.
Yes, sir. All right, sir.
Yeah, man. So
Yes,
tomorrow,
sir.
yeah, tomorrow we'll pick it up. And tomorrow I pick it up. And we'll finish off the notes tomorrow and start doing questions. As I said, Wednesday we'll do a class activity, similar to what we did with the transformation. A little bit different, but kind of similar. That will help us to understand it a lot more. Sunday we'll do a lot of questions, and then we give our classwork. And then after that, I'll be looking to do the revision. Either we're going to do the revision or we're going to do the first part of trigonometry before the revision. I'll decide. Either we're going to do the first part of trigonometry and then the revision, or we're going to do the revision first and then we do the trigonometry. All right, so we'll see. But that's it for today. Remember, watch over the video when I post it. Watch over the video, guys. Trying to understand everything that we have said so far. And tomorrow now is when we start doing the real stuff that will be tested on tomorrow. All this so far is just information. We're just building on it. Tomorrow is when we're gonna start doing the things that they'll, really ask a question about. It's a very easy topic, believe me, very easy. It's just basically how you get from one point to another point on a graph or on a diagram. That's what it's about. All right, it comes down to that. As simple as that, believe me. All right, so remember, guys, everybody on probation now with respect to doing the work. Everybody on probation. So if I don't get the work, I'm gonna put you out of the class. All right. If I'm not getting the work from you, I'm gonna put you out of the class. So make sure I get the work from everybody. All right. So we're not here. All right, guys, that's it. All right, we picked up back tomorrow afternoon.
Yes, sir.
All right, then.
Yes,
Cool.
sir.
Bye.
Okay,
All right,
Dad.
bye, everybody.
Bye, sir.
Bye, Dad.
Bye, Princess. Watch
Bye.
over the videos, everybody. Bye bye.
Okay.
Watch over the video. Watch over the video. Okay.
All right, sir.
All right. Cool.
Um.